All right, strap in, everyone, because today we're going deep.
Deep.
Deep. We're talking about energy and space-time,
Mm.
but not just the usual, like, oh, gravity bends light. Like, that's cool, but we're going way past that.
Yeah.
Past even Einstein's general relativity. I mean,
Beyond Einstein.
beyond, which is, a tall order, but that's the whole point of these deep dives.
Absolutely.
Yeah, and the source material that's got us all fired up is this document called, get this, General Relativity 2.txt.
Catch you?
Super catchy. And dense. Like, really dense. But, that's what we do here. We unpack it, we chew on it, we try to make sense of it.
Or at least.
At least sound like we do. So, you ready to get our minds bent a little?
Born ready.
Okay, good, because this is some pretty wild stuff. So, Einstein, right. General relativity. Everyone remembers the basics.
Bowling ball on a trampoline.
Exactly.
Yeah.
Massive object, like a planet, warps the fabric of space-time. And that warp, that's what we feel is gravity.
Yeah, and it's been amazingly successful. I mean, we've used it to predict everything from the bending of starlight to black holes.
Right, black holes.
But the thing is, it works great on these huge scales, like planets and galaxies.
Uh-huh.
But when you zoom in, way in, to the level of particles...
Like subatomic particles?
Yeah, like electrons and quarks.
Okay.
That's where general relativity starts to kind of, I don't know, break down a little. It doesn't quite fit anymore. And that's where our deep dive starts to get really interesting, because the document we're looking at, it talks about this idea of geometrising energy.
Okay, geometrising. That sounds complicated. It sounds fancy, but it's actually pretty simple. At least the idea is. Basically, it means understanding energy in terms of shapes and forms.
Okay, so like energy has a shape.
Exactly. Think about it. We're used to thinking of energy as this kind of abstract thing, but what if it actually had a physical structure? What if we could see the shape of energy, just like we can see the shape of a chair or a table? Well, hold on. So you're saying, like, my energy, like my personal energy, has a shape?
Yeah, potentially. Everything has energy, right? And if energy has a shape, then everything, including you, would have a corresponding energy shape. And that shape would determine how that energy interacts with the universe.
Okay, my mind is officially blown. So this is way more than just like a star-warping space-time.
Way more. We're talking about understanding the fundamental building blocks of reality itself.
Okay, but how do we even, like, study that? I mean, were you talking about, like, microscopes or something?
Not quite. You see, the problem is that our current models, even Einstein's, they describe energy using these abstract mathematical tools.
Tools?
Yeah, like equations and matrices. Things like, well, the energy momentum tensor, for example.
Okay, the what tensor?
The energy momentum tensor. It's basically a mathematical recipe that tells us how energy and momentum are spread out in space-time, but it's still just math. What we need is a more material description of energy. We need to understand what energy is actually made of, what its substance is, in order to truly geometrize it.
So it's like we have the blueprint for a building, but we don't know what the bricks are made of.
Perfect analogy. And one of the biggest mysteries is how to do this for fermions.
Fermions. Now there's another.
Yeah, another fun word. Fermions are basically the fundamental particles that make up all the matter we see around us. Electrons, protons, neutrons, all fermions.
Got it.
And we haven't figured out how to describe them geometrically without using these clunky mathematical matrices.
So it's like fermions are a missing piece of the puzzle.
Exactly. And if we can crack that code, figure out how to describe fermions purely in terms of their geometric shape, then we might finally be able to unify general relativity with quantum mechanics.
Which has been like the holy grail of physics forever, right?
Pretty much. It would be a revolution in our understanding of reality.
So what would, like, a breakthrough in this area even look like? I mean, what kind of crazy technologies could we unlock?
It's hard to even imagine. But think about it. If we can understand and manipulate the shape of energy itself, then who knows what's possible? We're talking about exploring the very fabric of reality.
So we've gone from Einstein and his warped space-time to, like, the cutting edge of theoretical physics.
Yeah, it's been quite a journey.
It has. And the crazy thing is, this is just the beginning. Who knows what other mysteries are out there waiting to be uncovered?
Exactly. And that's what I love about science. There's always more to learn.
Absolutely. And who knows, maybe one of you listening out there will be the one to make the next big breakthrough. Maybe you'll be the one to finally figure out the shape of energy and unlock the secrets of the universe.
No, that's a thought to ponder. I mean, if energy does have a shape, then what does that shape even look like? Is it something we can even comprehend with our current understanding of the universe?
Good questions. And ones that I think are going to keep physicists and all of us busy for a long time to come.
Absolutely. So keep those brains buzzing, folks. The search for the true nature of energy, it continues.
It does indeed. And we'll be right here, ready to dive deep into whatever crazy new discoveries come next.
Can't wait. See y'all next time.
Yes.